Okay, picture this. You've got an insanely powerful AI model, but making it do exactly what you want costs an absolute fortune in computing power. It's a huge bottleneck. Well, today in this explainer, we're decoding a true landmark in modern artificial intelligence that literally changed the game. It's a seminal paper out of Microsoft research called LoRA, Low-Ranked Adaptation of Large Language Models. The researchers basically found this incredibly elegant mathematical shortcut that completely overhauled how the industry handles massive AI models.
So, here's our game plan for today. We'll start with the giant AI problem we're facing. Then, we'll look at the LoRa solution and how it actually works under the hood. After that, we'll check out some real-world adaptation examples, unpack the results and trade-offs, and finally, we'll hit the big takeaways.
All right, let's dive right into section 1, the giant AI problem, and why fine-tuning massive models is frankly breaking our hardware.
Here's a question for you. How exactly do you retrain a brain with 175 billion connections? Think about a massive general-purpose model like GPT-3. It's got 175 billion parameters. Now, imagine you want it to be really, really good at one specific downstream task, something like writing SQL code or summarizing messy medical documents. The traditional way to do this is full fine-tuning. You initialize the model, and you actually update every single one of those 175 billion parameters. But here's the logistical nightmare. Storing and updating a custom 175 billion parameter model for every single little downstream task you have, it is completely unscalable.
Just to put this in perspective, 1.2 terabytes. That is the VRAM, the sheer GPU memory consumption required just to do a standard full fine-tuning of a model like GPT-3. Because you aren't just storing the weights, right? You have to store all the optimizer states and gradients for every single parameter. For most researchers and everyday companies, that is just prohibitively expensive. It basically locks the most powerful models behind this massive million-dollar hardware barrier. Which brings us to section 2, the LoRa solution, a very clever mathematical shortcut.
Let's think about this with a simple analogy. Full fine-tuning is kind of like taking an entire massive encyclopedia and handwriting a brand new, slightly altered copy of the entire book just because you wanted to fix a few paragraphs. It's overkill. LoRa, on the other hand, is like keeping that original printed book exactly as it is and just slapping a tiny sticky note on the page with your corrections. You don't touch the original text at all. But when you read the page, you read the printed text plus the sticky note. So, in AI terms, instead of updating all those pre-trained parameters, we just append a tiny amount of new task-specific information.
So let's translate that sticky note into the actual technical definition. LoRa stands for low-ranked adaptation. The researchers had this brilliant hypothesis. They figured that when you adapt a massive model to a specific task, the actual change you need to make to the weights doesn't need to be massive. It has what they call a low intrinsic rank. Basically, the specific knowledge needed to learn a new task operates on a much, much lower dimension than the original model itself. So what LoRa does is freeze the pre-trained model weights entirely. No gradients are calculated for them whatsoever. Instead, it injects these tiny, trainable rank decomposition matrices into each layer of the transformer.
Okay, moving to section 3, how LoRa actually works. Let's look at the step-by-step methodology.
Here's the logic flow. Step 1, the input. We take the pre-trained weight matrix, called W, and we completely freeze it. It's locked. Step 2, the process. In parallel to that, we inject two very small matrices, which we'll call A and B. Matrix A starts with a random initialization, and matrix B starts at straight 0. Now, here's the magic. These two tiny matrices are literally the only things updated during training. Finally, step 3, the output. We run the input through the frozen matrix W and simultaneously through our tiny A and B matrices, and then we just sum them together. So your new forward pass is simply WX plus BAX. Because A and B have a rank of sometimes just 1 or 2, the compute power required just plummets, but the model still learns exactly what it needs to for the task.
Let's see this in action. Section 4, real-world adaptation examples, from natural language all the way to structured data. Check this out. For a highly complex task like WikiSQL, which is translating natural text into SQL queries, traditional fine-tuning would force you to update 175 billion parameters. LoRa updates just 37.7 million. And the outcome? LoRa actually beats the full fine-tuning approach in accuracy. It's wild. Or look at Samsung for conversational summarization. LoRa uses a measly 4.7 million parameters, and again, beats the fully fine-tuned 175 billion parameter beast. Even when you pit it against older efficient methods, like adapters in the E2E data-to-text challenge, LoRA uses just a third of a million parameters and still scores higher. It is wildly efficient, and you don't sacrifice a single drop of quality. So what do these numbers actually mean for us? Section 5, Results and Trade-offs. Let's unpack the metrics. Look at this massive difference. We are reducing the number of trainable parameters by 10,000 times for a massive model like GPT-3. We're going from 175 billion down to 37.7 million. That is quite literally the difference between needing a giant air-conditioned warehouse of GPUs versus something you can manage on much, much more accessible everyday hardware. And it scales beautifully. When we look at validation accuracy against the number of trainable parameters, notice those bottom lines for prefix tuning, which is an older method of efficient adaptation. See how the lines start curving down? Basically, if you add too many parameters in prefix tuning, the performance drops off because it gets too difficult to optimize. But look at the LoRA line, holding strong right at the top. It scales gracefully. It stays incredibly stable and highly accurate no matter how many trainable parameters you tweak it to use. It simply doesn't break when you push it. But, quality isn't everything. Speed matters tremendously when you actually put these models into production. Older solutions, like adapter layers, have to be added sequentially. That means the data has to wait to go through the base layer before it can even hit the adapter layer. And that creates a serious traffic jam, causing up to a 30% slowdown in inference latency. LoRA completely bypasses this. Remember that equation WX plus BX? Because it is just simple linear math, when you're ready to deploy, you can literally just add the A and B matrices directly into the frozen W matrix. You just merge the weights. The result? Exactly zero additional latency compared to the original base model. So, what's the bottom line? Section 6, the big takeaways, and why this fundamentally changes the AI landscape. Let's quickly recap these massive wins. Number 1, your VRAM consumption to train drops from an impossible 1.2 terabytes all the way down to 350 gigabytes. Number 2, and this is absolutely huge for real-world deployment, your task-specific checkpoint size shrinks from 350 gigabytes down to a tiny 35 megabytes. Number 3, as we just saw, there is zero added latency during inference. And number 4, it enables instant task switching. You can host one giant frozen model in the cloud and just hot swap these tiny 35 megabyte LoRA modules in and out of memory on the fly for totally different users doing totally different tasks. Now, to be completely fair to the research, we have to talk about the limitations. The authors themselves point out that if you do merge the A and B weights into the main model to get that zero latency we talked about, it becomes mathematically tricky to process different tasks simultaneously in a single batch. Like if user A wants summarization and user B wants SQL generation, you can't easily batch them together in one pass if the weights are already merged for just one of those tasks. You'd have to keep them unmerged and load them dynamically, but then you lose the zero latency benefit. So it's a bit of a trade-off between latency and batched task flexibility. Even with that trade-off, the implications of this paper remain utterly staggering. As we wrap up this explainer, I want to leave you with this thought. We are already moving from billions to trillions of parameters in our base models right now. As these digital brains get incomprehensibly large, do parameter-efficient adaptations like LoRA become more than just convenient tricks? Are they actually the fundamental key to making personalized AI accessible, affordable, and scalable for everyone on Earth? Think about it. Thank you so much for learning with me today. Until next time, stay curious.